our goal is going to be able to count how many juggling patterns there are, and we kind of have a vague process in mind because we know we have these minimal juggling patterns and we want to build up and make all juggling patterns. So one of the things that we need to get a good handle on is what we can say about how many minimal juggling patterns there are with K balls. So that's our goal for today, is to explore these numbers a bit. Now these numbers have been known for quite some time, although not in the context of juggling. They arise in other locations. These are called the Eulerian numbers. Now Eulerian means it traces back to Euler. Now you might see that E-U-L-E-R and think, shouldn't that be Euler, like Euclid? And no, it's Euler. I made that mistake when I was a young mathling, and I often thought, oh, here's this Euler guy, he does a lot. No, it's an Euler. And he's an amazing mathematician, highly productive, would produce nonstop mathematics. Even after going essentially blind, he still kept producing mathematics. And he's considered one of the great mathematicians that ever lived. And so what are these? So here's how we're going to define them. So we have the Eulerian number nk, and it's denoted with these angled brackets. So these aren't the parentheses that we saw for binomial coefficients. They're angled, a little bit of a corner there. And it's the number of ways to place n non-attacking rooks on an n by n board. So in other words, we're populating the board as much as possible with k rooks below the diagonal. Now on a side note, this is not the way that most people define the Eulerian numbers. It is defined in a slightly different context. We'll talk about that on a different day. But for our purposes, that's how we're going to define it. And so from what we talked about in terms of minimal juggling patterns, this is the same as how many minimal juggling patterns are there of period n using exactly k balls. So that's how you can think of it. We're going to talk about rook placements today. Now, what can we do? Well, we can generate data. So here's some basic data. So if we have a 1 by 1 board, well, there's no below the diagonal. There's just one square, so it's 1. For 2 by 2, 1, 1. For 3, 1, 4, 1. It's not so hard. In fact, here you'll see down there all of the possible 3 by 3 placements of rooks. And you can see, okay, there's one placement where no rooks are below. There's one placement with 2 rooks below. And there's 4 placements with 1 rook below. So that's where you get the 1, 4, 1. And then continues on. 1, 11, 11, 1. 1, 26, 66, 26, 1. And so forth. Now, what do we see? Because one of the things that we have is once we have data, we like to say, hey, let's explore a little bit. Let's see what are some things we can say. Now, one thing we can look at and say, well, what if we add across here? What do we see? So, for example, adding here, we get 1, 2, 6, 24. All right, those are ones we can do sort of in our head, without hardly any pause at all. How about this one? Now, we could say, okay, let's add these numbers. Or we could say, well, wait a second, hold on. These numbers, 1, 2, 6, 24, these aren't just any numbers. These are numbers that we've seen before. And in particular, what we're saying is, hey, we're looking at all of the ways to place the rooks on the board. And we know that. It's n, or rather n factorial. So, for example, 6, 3 factorial. 24, 4 factorial. So 5, if we add, we'll get what? 5 factorial. Yeah. And here, 6 factorial. So we can either add up the numbers or know that 6 factorial is 720. So there we go. There's a pattern. All right. Now there's some other things to see. For instance, there seems to be some symmetry here. In other words, if we go one way, it's the same as if we go the other way. All right. Great. Well, why? It's not so obvious. It's a little subtle here. And we'll talk about that as well. Now, one thing you might notice is that these entries here are all blank. Now, a blank entry corresponds to 0. Why is it 0? Why is it 0 over here? So, for that, let's talk about a wonderful, beautiful idea. And it's a very fun idea. So this is called the pigeonhole principle. Now, what is the pigeonhole principle? Here's a very fancy way of saying it. So suppose you have a collection of objects, and we'll say that there's S objects, and you're putting them into T groups. Okay, so S is the number of objects, T is the number of groups. Now you might say, well, what's the average number of elements in a group? We take the total number of objects divided by the total number of groups. It's S over T. And now the pigeonhole principle says, look, some group has at most S over T objects, and some group has at least S over T objects. In other words, there has to be something which is at or below the average. There has to be something which is at or above the average. So put it another way, the pigeonhole principle says not everything can be above average. Now, I don't want you going and saying, oh no, Steve says that I'm below average. I don't want you to take that message. What I am saying is that we can't all be above average in the same thing. It's true. The math just doesn't support it. But what is true is that there are many different things out there. And so you might not always be above average in everything, but you'll be above average in something. So yes, you're still special. Okay, good. Now, how does this pigeonhole principle relate? Well, what's going on here is we want to say, okay, what are our objects? What are our groups? And you might say, okay, we can think of the objects as the pigeons, right? And the groups as a whole. That's not what quite pigeonhole is, by the way. In terms of like, where does the phrase pigeonhole comes from? If you go look at some old desk, you'll see they had this little thing on there where you could stuff, like to put in documents and so forth. You'll see this, for example, in old pirate movies where there's captain's office and there's places to stuff. So this was what was called the pigeonhole. So the idea was, if you had too many things, something had to be in common. Okay, so essentially, the way you apply pigeonhole principles, you think, okay, what are the objects and what are my groups? Sometimes they're given to you, sometimes you have to sort of add them into the problem. So here, what we'll do is we'll think of our objects. Those will be our rooks. And we can think of our groups. Okay, those can be our rows. So we have rooks and rows. All right, now, what do we see? Okay, so let's suppose we look at nk, and let's have k be greater than or equal to n. So in other words, we're looking at our table, and we're looking at the spots where k is very large compared to n. Now, what happens? Well, notice what are our objects? There are rooks. We have k of these. Now, what about our rows? Well, our rows, that's where we have to put them in, and those are below the diagonal. So, in particular, there are n minus 1 of those. Because if we're just focusing on where can we put the rooks below the diagonal, we have one less row available. And so, on average, it says what? Well, that says there's k over n minus 1 rooks per row below the diagonal. Now, you're like, okay, great. Well, how does that help us? Well, the way that helps us, we say, oh, wait. Here, k is strictly bigger than n minus 1. So because k is greater than or equal to n, that's strictly bigger than n minus 1, which means that k over n minus 1 is strictly bigger than 1. And now we say, aha, some row has to be at least that average, right? That's the Pigeonhole principle. Something has to be at least the average. So some row has to have an average that's above 1. Well, if you're a whole number and you're above 1, that means you're at least 2. That says some row has to have at least 2 rooks in it. But that can't happen because then those 2 rooks are going to clash. They can attack each other. And therefore, impossible. So the Pigeonhole principle, it's a really amazingly beautiful idea. And it sounds so simple that you might think, well, there can't be much interesting math that comes from it. And we certainly have applied it in a very, I don't want to say trivial way, but a very basic application. That said, there is interesting math that connects back to the Pigeonhole principle. So it's amazing how very simple ideas can be very powerful. It's just a matter of knowing how to use them. All right, good. So because of the Pigeonhole principle, we can now say that that's why these entries are 0 and all these entries are 0 over there. All right, so that's something. All right, well, what are some things that we want to talk about in this session? We're going to talk about 3 things. So the first thing is we're going to talk about symmetry. Why is it that we see these symmetrical numbers going around? So in other words, the Eulerian number nk, why is it the same as the Eulerian number n minus k minus 1? Okay, we'll see that. The next thing is we're going to talk about a recursion formula. Now we've seen recursion formulas before. For binomial coefficients, it was very simple. For straight numbers of the second kind, well, it became a little bit more complicated. For these Eulerian numbers, we're really going to go up and make it a lot more interesting in some sense. So the Eulerian number nk is k plus 1 times the Eulerian number n minus 1k plus n minus k times the Eulerian number n minus 1k minus 1. Which says that really you can go down row by row and populate all these numbers in. You just have to be patient and apply the rule. So if we have the data for the row for 6, which we do, we can then put in the row for 7. And then once you have the data for 7, you can put in for 8 and go as far as you want to, as much as you're patient for. And we'll actually see why this is true as well. The third thing we're going to talk about is something called Werepitskys identity. Now, it sounds a little strange. Well, what does it say? Well, it says if I have x to the power n, that's the sum of the Eulerian number nk times this sort of binomial coefficient looking thing, x plus k, choose n. And you might say, well, when I see a number like x, I think of x like as a variable, like it could be any number. It doesn't have to be a whole number. And the answer is yes, in fact, it's true. And we'll talk about what that means, why we would care. We won't prove this, but I will say if you're interested in proofs, you can start with the recursion. And once you have this recursion, the proof comes out. It's a little bit of induction, nothing too terribly fancy. There's a little bit of a small subtlety at the start, but not so bad. So what we will talk about with Werepitskys identity is how you can apply it and get some really rather interesting results to come out. All right, so there's our goal. 3 things for us to talk about. Let's begin. So our first thing is we're going to talk about our symmetry. And here's how we're going to think about it. We're going to do what's called a bijective proof. Now, what does that mean? Well, the notion of a bijective proof is to say, look, I want to find a pairing. And so if I want to show 2 things are equal, what I can do is say, okay, if I have a set of objects, so I have this big universe of objects here, and what I'll say is for everything I have here, there's a unique pair there. So there's this sort of 2-way going back and forth. So there's a one-to-one relationship. So that's the idea of bijection. I can do a pairing. So I'm going to pair everything where I have k rooks below on one side with over here where I have n minus k minus 1 rooks below on the other side. So how are we going to do that? So here's the idea. We're going to start with our board here. You'll notice our pink region there. That's our region below the diagonal. So that's where we care about where the rooks are. And then we have the green region, which is stacked on top, and then this extra column on the end, which for right now we don't color. We won't need to. So we're going to do two things to our board. The first thing is we're going to move this last column to the first column. In other words, we'll just pick it up, move it across. Okay? Not so bad. Great. Now that we've done that, we say, okay, what do we have? Well, we've just essentially shifted over our green and our pink. No problem. No problem. Now, what we're going to do is we're going to take the diagonal here and we're going to flip it across. So it's like you come in with a spatula, put it underneath, lift it, turn it over, put it back down, like you're flipping a pancake. And we're going to flip it right across that line. And so what happens is that this green region here, when you flip it, goes right into that part. Notice, where is it? It's the part that's now below the diagonal. And so, and now the pink region is off to the right, and this, what was the first column, now becomes the first row. Okay, so that's the board manipulation. But really what's happening is we're going to be doing all of this while we have a rook placement. So imagine that we had some rook placement. So let's actually do this. And it's easy to imagine something if we actually go through and carry it out. We just have to be patient here. And so, placing rooks. This is when you say to yourself, I should have chosen a smaller board. Well, that's all right. The point is, we just need to make sure we have some rook placement. Okay, so while we're doing our moves on the board, we're going to be doing it with the rooks in place. So what does that tell us? Well, what it tells us here is that every move that we did, it's preserving the rook placement. So in particular, if I had a valid rook placement before, I still have a valid rook placement after. No problems. No problems at all. All right, great. So, there we are. So there's what happens when we take that first column and we move it to the end, okay? Doom. If we had a rook placement before, we had a rook placement after, right? Because that column still has a rook in it and still only has one rook in it. And the row, well, look, it's still in the same row. So great, no problem. Now we flip, okay? And the key here is we only had one rook in each row and one rook in each column. Well, now you have one rook in each column and one rook in each row, because when you flip, the columns and the rows interchange. And so, lo and behold, we are going to be able to have a rook placement. And, okay. So, all right. Okay. Sorry, this is the part that makes you say, why did I choose an 8x8 board? Should have chosen a 4x4 board, because it's easier to keep track of what's happening in a 4x4 board. But that's okay. It's good for us to actually see how everything works out. All right. And there we go. Okay. Now, how does this all fit together? Well, let's think about it. Let's suppose we start and there are k rooks, which are in our pink region. Okay. How many rooks are in our green region? And how can we figure that out? Well, if we think about it, we say, well, look, collectively, the pink and the green used how many columns? Well, n minus 1, because there's this last column here which isn't involved. All right, so collectively, those two regions are going to have n minus 1 rooks in total. I know how many are already in the pink, so that means that for the green, I have to have n minus 1 minus k, because I need a total of n minus 1 between the two. And now, what's the other thing that happens? We'll notice here, the pink region is what's below the diagonal. By the end, it's the green region. So, by doing these two steps, what we've done is we said, okay, if you start with k rooks below here, you'll have n minus 1 minus k rooks below there. So there's this matching. Boom, boom. And you do this with every single pair. And notice, of course, we can even run backwards. So if you have n minus 1 minus k, you can, of course, flip across, and you can move the column. And now, again, it's this matching. So there's a 1-to-1 matching between the different kinds of rook placements. Which means what? Well, if we can pair them up 1-to-1, it has to mean that the total numbers are the same. So the conclusion, the thrilling conclusion that we get from this is that the nk, Eulerian number, nk, number of ways to place k rooks below, is the same as n and then n minus 1 minus k. And that's the symmetry. There we go. Bijective argument. Beautiful, beautiful idea. The next thing we want to be talking about is the recursion. And so there's a couple ideas that we want to sort of set up. And once we have those ideas set up, it's not so bad. So what are the couple of ideas that we want to set up? Well, first off, imagine that you have a big board and you have two rooks somewhere on that board. It doesn't really matter where they are. And remember, these rooks are non-attacking, which means there's no two rooks in the same row, no two rooks in the same column. So here, I've marked the two rooks. And so those are the only rooks in those rows and the only rooks in those columns. Now you'll notice something, and that is that there's this sort of natural rectangle here. And that the rooks are currently on opposite corners. But there's another pair of opposite corners. So what you can do is you can move the rooks. So in particular, I can take those two rooks and move them like so. And the net result is I have another rook placement. Perfectly valid. Because again, there won't be two rooks that attack each other and everything's good. So there's this sort of modification to rook placements. In fact, with patience, you can get from any kind of rook placement to any other kind of rook placement by this sort of swapping out very slowly. Now, we're not going to do that in general. What we are going to do is focus on very special case. And the very special case that we want to focus on is putting a rook down in the very bottom corner. Now, it's possible that the rook is already there to begin with, in which case we're like, woohoo, life is good. Yes. But it's also possible that it's not. So, if the rook is there, no need for a swap. What if it's not there? Okay. Well, if it's not there, then what we do is we say, all right, let's take a look at our board. Then it must be the case that there is somewhere a rook in the bottom row, and it can't be in the corner. And there has to be somewhere there's a rook in the last column. It can't be in the corner. And now we swap those pairs of rooks, and we're good to go. So that's how we know, with at most one swap, we can get our position, our board, to look like that. Now, what's the nice thing here? Well, the nice thing here is, look, if I have an n by n board, and I say down here I have this one rook that takes care of these last row, last column, then what's left is up here, there's a smaller board, an n-1 by n-1 board. Okay, well that's good. That's actually fantastic for us because it says, oh, it's like I can get down to a previous case. In fact, that's the key idea. It's like I can reduce down to a previous case and say what's going on. But we're going to reverse it and say, okay, so what does that mean? Well, it means that every single n by n board can be done in the following way. You start with an n-1 by n-1 board. Then you add in this padding here with one rook in that corner. And now you say, okay, either leave that rook where it is or do a swap. And you can swap in lots of different ways, because there's n-1 rooks up here. So you have all these different swaps. Every swap gives you a different rook placement. And this will generate every single rook placement. And so we have perfect. You see, when you're trying to deal with recursion, what's the idea of recursion? The idea is to connect back to a previous case. And that's what we're doing. We're saying, oh, we really are interested in the n by n board. We're able now to connect back to the n-1 by n-1 board. And that's what enables us to make progress, to get a formula. And that is good news for us. So there are going to be three possibilities that we need to talk about. Either we don't do any swap, we do a swap, but it's going to be below the diagonal, and we do a swap and it's on or above the diagonal. And we want to understand what's happening in each one of these cases. Okay, so let's talk about our first case. So that is, we're going to do no swap at all. So in other words, this is what our picture is going to be. Now, the question is, what can we say about the number of rooks which are below the diagonal? Well, notice that this rook is still on the diagonal, so it's not below it. And so the rooks which are below the diagonal are coming just from here. So in other words, it has to be the same number of rooks that were below the diagonal of the board that you put in, that n-1 by n-1 board. All right, now what does that mean? Well, suppose we're after nk. Okay, that's our goal. So if I don't want to do a swap and I want to have k rooks below the diagonal, that means I need to have k rooks below the diagonal in what I put in. So that's going to be an n-1 k, right? The n-1 is because we have a smaller board, and the k says I need k rooks below the diagonal because I'm not going to gain anything or lose anything. And so there you go. All right, good. So that's the first case, one case down. Well, there's going to be more, so that we're not done yet here. This is an equation that's in progress of being determined. All right, so let's go to the second case. Let's do a swap below the diagonal. So suppose I had a rook here. That's below the diagonal because I'm going to swap it with something in here. And now what happens is when we think about completing our rectangle, that says that after our swap, we're going to have our new rooks in these locations. Now what happens? Well, notice that here, this rook, you can think of as moving up here. It's still not going below the diagonal. And this rook, well, that's going below the diagonal, but it started below the diagonal. So in other words, it still has the case where I don't change the number of rooks below the diagonal. So if I do a swap with something below the diagonal, the total number of things below the diagonal stays the same. Good. So what does that say? Well, that says, look, we really want to have here, when we put in this board, we want to have k rooks below the diagonal. Okay, so we're going to have, again, this n-1 k. Now, there's one other thing we need. What can we swap with? Well, we can swap with any of those rooks below the diagonal. How many are there for us to choose from? And the answer is, there's k of them. And so that has that factor of k. So in other words, put in a board with k rooks below the diagonal, pick one rook below the diagonal, and now do a swap. So there's their board, there's the rook we chose, and therefore we get this many contributions for our n by n board. Okay, one more case, and that's what if we do something that's on or above the diagonal? Okay, so, well, what's that going to be? So suppose I take a rook up here. All right, and we do the swap, and what happens? Well, what happens is something a little different this time. Notice that we gain one rook below the diagonal. You see, this rook you can think of as going down, and now it's below. And this rook wasn't below, and it still stayed, not below. So we have a sort of a +1, which means what? Well, that means that when we're looking here, we're going to have not k rooks below, but we want to put in something with k minus 1 rooks below, because we're going to increase it by 1. Okay, so in this third case, we say, okay, what happens? Well, we're going to put an n minus 1 board, but we want k minus 1 rooks below. Again, that k minus 1 is going to become k after we do the swap. Now, how many things can we swap with? All right, let's do our count carefully here. We know how many are below the diagonal. It's k minus 1. How many rooks are there in total? Well, it's a n minus 1 by n minus 1 board, so it means there's n minus 1 rooks in total. So you can think of this as there's n minus 1 rooks in total, but we can't swap with any of the k minus 1 rooks below the diagonal. So it's going to be n minus 1 subtract k minus 1. Or, when you clean this up, because you can get the minus 1s to cancel, it becomes n minus k. And now we have our pieces. So the total number of n by n boards with k rooks below the diagonal, well, it's n minus 1k. That's if we don't do a swap. K times n minus 1k. That's if we start with a smaller board with k rooks below and we swap with something where we have a rook below. And n minus k times n minus 1k minus 1. And that's if we start with something slightly smaller, one smaller rook below, but we swap with something above the diagonal. So we put this together and we come up with, well, these two can combine. So k plus 1, n minus 1k, and then plus n minus k times n minus 1 k minus 1. That's it. That's it. There you go. Okay, so that's the recursion. All right. I will say this is a very unusual way to do the recursion. Almost all recursions for Eulerian numbers are not done using this philosophy of rook placements. We'll talk, again, more about Eulerian numbers in a different session and show that, oh, yeah, there's actually a different way to think about it. And it's like, those cheaters, they're doing it too easy. We're letting them off. But I still think this is really kind of a fun idea because it sort of emphasizes philosophy, right? What are we trying to do? Well, we're trying to relate a previous case to the current case. And how can we connect the two? What's an operation to get from one to the other? And that's an important idea in mathematics. How do you build off of a previous case to get a slightly larger case and then keep going? Now this brings us to our last thing that we want to talk about, which is Werepitskys' identity. Now I will say Werepitsky was actually not the first person to come up with this. This was discovered, I think, about 15 years before by a Chinese mathematician. Unfortunately, as often happens in mathematics, credit is not always given to the first person who discovers it. That's an unfortunate side effect. You'll discover it's kind of an interesting thing in math, and I don't want to get into too much of a discussion here. It's a lot of math gets discovered, and then it gets rediscovered, and then it gets rediscovered, because good ideas are often repeated, and it's not very unusual for people to have similar ideas. And back, 150 years ago, it was very hard for people to communicate what they were doing. And of course, nowadays it's slightly better. The problem with math today is not that we don't have good communication, it's just that we have so much math. There's a lot of it happening. And so it can be very challenging to make sure that you stay completely up to date. So, okay, Werepitskys identity, we'll call it Werpitzky. What does it say? Well, it says, suppose you have x to the n. Well, you can rewrite this in terms of the sum. And when we write a sum without any bounds, it just says sum over all the possible values, where we have an Eulerian number times something that looks like a binomial coefficient. And we would say this is x plus k, choose n. Now, if you took a calculus class that talked about binomial series, you hopefully saw this. And what does this mean? Well, what it really means is that we're going to have a fraction where we're going to multiply n things on the top and n things on the bottom. Now, what you get on the bottom is really n factorial, but you can just read it off, okay, as n times n minus 1 times times n minus 1. Okay, so it's n factorial. Now, upstairs, what you'll do is you'll really have something very similar, and in that you're going to have n things multiplied. And what's going on when you have that n factorial, see n minus 1, n minus 2, you keep going down by 1 every step. So we're going to do the same thing. So we're going to start with x plus k is the first thing. Then we're going to subtract 1, x plus k minus 1. The next term would be x plus k minus 2. And all the way down to the end, x plus k minus n minus 1. And so what's the net effect? Well, the net effect is to say, hey, I can take this thing that looks like a really simple polynomial term, x to the n, and rewrite it as a combination of these other things that are polynomials. And our first initial reaction to this is like, this is terrible. Look how complicated you've made this. Why have you done this to us? But after we get over our initial reaction, we're like, say, okay, well, maybe there's a good reason to do this. You see, there's this sort of idea that if you can change an expression, you might be able to change it into something where it's easier to carry out certain operations, certain computations become simpler. And in some sense, it's saying, well, let's try to rewrite this power here of x as something that behaves like a binomial coefficient. And perhaps there are certain things where when we express it in terms of these binomial coefficient looking things, where we get a lot simpler operation. And it turns out there is. And let's take a look. So we're not going to give a proof of Werepitskys identity. It follows by induction, but we are going to show you an application. So the first thing is we want to show you, hey, there's something you can do with binomial coefficients which is really, really easy. And now we're going to be like, well, that's good. So we can say, okay, we can transform a problem of adding things which are difficult to a problem where adding things is easy. And so it's like, woohoo, we can solve it. So that's where we're going. Okay, so that's our roadmap. So first step, what can we do with binomial coefficients that's very easy? It turns out the answer is we can add binomial coefficients in certain ways very, very simply. Now, in particular, it says, suppose you have a sum, and I'm actually telling a start and stop point, from 0 up to m of I choose k. And the answer is m plus 1 choose k plus 1. So in other words, what's the picture here? Well, the picture says the following. All right, suppose you pick some k. So in other words, we're adding down a column, and then we're going to stop. Okay, so we're adding down our column, and then we stop. And I want to say, well, what's those numbers when we add them all together? And the answer is, it's going to be that number right there. So, in other words, 1 plus 4 plus 10 plus 20 plus 35 is 70. Is it? It is. It is. And when I learned this, the teacher who taught me this called this the hockey stick identity. Because if you're familiar with what a hockey stick looks like, it looks vaguely like this shape, where you have this long part, and then you turn it a little bit at the end. Now, that's always going to be the case. So, for instance, here, we can go over and say, well, what if I went 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8? What's the answer? It's 36. And it is. It'll always work. Now, I'll do a proof by picture, but then I'll also give you a sort of an outline for another proof. So what's the proof by picture? Well, let's go back to the 70. So remember the recursion? The recursion says you got the one up above to the left and the one straight above. Say, okay, great. Well, I'll keep this one, but then this one straight above, I'll go above to the left and straight above. Okay, I'll keep the 20. And now I'll keep going up. Okay, so I'm going to be the 10 plus the 5. I'll keep the 10. And here, the 5 will be the 4 and the 1. Okay, I'll keep the 4. And then the 1 I'll replace by the 1 and the 0, right? And then, of course, from there, you can just keep going. And it'll be just a bunch of zeros. And you just work your way out. So, lo and behold, you say, look, it's like I'm adding the one above to the left and the one above, but I only ever keep the one above to the left, and the other part I just keep going up. And that's sort of the picture of why it's true. All right? And that's actually a reasonable argument, and I'd be satisfied with that. Here's another argument. It's a combinatorial proof argument. You say, okay, what am I looking for? I have m plus 1 objects, and I want to pick k plus 1. Okay, so that tells me what I'm trying to count. Okay, so there's, let's say the numbers 1 to m plus 1, and I'm selecting k plus 1 numbers. And now what I'll do is I'll group them based on what's the largest number. Okay? And I'll call the largest number, well, let's suppose we call it I plus 1. Okay, all right, sure. Okay, we'll call it I plus 1. Now, what's true? Well, if I plus 1 is the largest number, that means all the other numbers have to be smaller. Yeah, okay, that makes sense because you picked the largest. Well, I need a total of k plus 1 numbers, which means I need to pick k numbers left, and they all have to be at most I, so that means I have to pick them from among I. So I choose k. So in other words, here, we're grouping where I plus 1 is the largest number in our group. And there we go. There's exactly I choose k ways where I plus 1 is the largest element. And now, of course, we just let I run from our possibilities. It could be anything up to m, right? Because m plus 1 is the largest number available. And that's a combinatorial proof argument. But what's the moral of the story? The moral is binomial coefficients are great to add. Now, how does this relate back to Werepitskys' identity? Well, if you think about what's happening when we talked about that binomial coefficient, like x plus k choose n, what we had is upstairs, it was really like x to the n power. And so it's like, oh, okay. So in some sense, it's saying, hey, here are easy ways to add powers, x to the n. And that's where the application comes in. All right, so let's take a look. We need two things to recall. So here we're going to do Werepitskys' identity, and I'm going to think of now as a whole number. So I have j to the power n is our sum, our Eulerian number nk, and j plus k choose n. And then we have our hockey stick identity, the one where it says, hey, it's easy to add binomial coefficients down a column. It just says if you add them down a column, you go one column over, one row down from where you stop. So there we go. So those are our two facts. And now what we want to do is we want to add up powers. So think of it as like 1 squared plus 2 squared plus 3 squared plus 4 squared. Or maybe like 1 to the 5th plus 2 to the 5th plus 3 to the 5th plus 4 to the 5th. Things like that. Now, that's a hard problem, right? Well, not if you have the right tools. See, that what we want to do is transform it to an easier problem. So here's the idea. So step 1, we're going to take our sum, where we have our nth powers, and we're going to say, oh, look, this I to the power n, I can replace it here with the Werepitskys identity. So this 1 here is just saying by fact 1. So it's our sum, I equals 0 to m, and then we have this expression where I've just replaced j by I. Okay, great. Now, a side note here. We have two sums. We have this sum with I, and we have this sum with k. And what we're going to do is reverse the sums. See, when we talk about these sums, we're just adding lots and lots of pieces together. And the question is, well, what should we be adding first? Should we add first with respect to I, then with respect to k, or first with respect to k, then with respect to I? And the answer is we can do either. Now here we're perfectly safe because there's only finitely many things. And ultimately what we're doing is we're just saying, oh, we're just rearranging the order in which we do addition. And when we have finitely many things, perfectly safe to do that. And so that's why we're perfectly fine. If you've ever done multivariable calculus, there's this sort of notion of, oh, we're like changing the order of integration, right? Here we're changing the order of summation. And it should feel similar because it's similar. But, all right, so here we go. Now, the important thing is it's easy to change these sums because in some sense they're independent. Like the sum over k has nothing to do with the sum over I. So they happen independently. So whenever those are independent, it's just as easy as whoop, and we're good to go. So change the order you add things together. Okay, great. We can do that. And now there's sort of our, oh, wait a second. Notice here on our new inner sum, what's happening? This is a sum where we only sum over I. This piece has no I at all. It's that Eulerian coefficient. It only depends on n, and it only depends on k. So this is a constant, which means it can go outside our sum. All right, so that's our second step, right? So we swapped the order of integration. We pulled out a constant. Wow, we're doing great. We're making wonderful progress here. And now we have our like, whoa, we are adding up binomial coefficients down a column. Now, of course, the tricky part is, these numbers don't quite match, but this is one of the things that you have to get used to in math, where you can change the names you call things. In fact, one of the great powers in math is our ability to change names. In some sense, that's what substitution is in calculus, is we're changing our names. And when you can get comfortable with this idea of like, oh, I used to call this one thing, and now I'm going to call it something else, you can get a lot farther in math. If you're stuck on saying, no, I insist, it always has to be the same, it's not going to be as fun. So, but we're going to be flexible. Say, okay, we know our name change. And so this says, hey, we're adding down a column. Now, this is a great time for you to object and say, wait, I'm suspicious here. Okay, let me hear your suspicion out before we proceed. My suspicion, my worry here is that while it's true we're adding down a column, isn't it the case here that for our sums that we're not starting at 0, we're sort of starting further down. because of this plus k. And to which I respond, oh, yeah, you're right. And my response is, we're okay. You don't have to worry about it. But you should sort of pay attention to these things. Why don't we have to worry about it? Well, the answer is, while it's true that we're starting not at 0, but a little bit further down, we're still in the part of the table where all the entries are 0. So even though we're starting further down, it doesn't matter because everything above it was still 0. So we're good to go. All right, which means by property 2 that adding binomial coefficients is easy. See, adding powers, hard. Adding binomial coefficients, good, easy, we like it. We can say, aha, that's simply m plus k plus 1, choose n plus 1. And we're done. Now, you might think, what is it we've done? What have you actually shown here? Well, what we've shown here is if I want to add up powers, that becomes a sum where we have a combination of Eulerian numbers and binomial coefficients. So this is sort of very abstract. Let's go very concrete. So we've rewritten the formula we just argued. And so this is the sum. 0 to m of I to the n is the sum over k, this Eulerian number, nk, and this binomial coefficient, m plus k plus 1, and choose n plus 1. Okay. So now let's do concrete examples. And so by that, what do we mean? Well, suppose you wanted to find the following. 1 squared plus 2 squared plus all the way up to m squared. So in other words, you wanted to add up a bunch of squares. Not so easy, right? It's not so obvious what's going to happen here. Okay, so what's happening here? Well, this is really the case where we have n equals 2, right? Because we're adding up squares. So according to the formula, so I'm just applying the formula here, this will be equal to, all right, so we're going to have n equals 2, and we add up over all k. Well, we only add up over the k where we can have the Eulerian number. So 2, well, we can have 2, 0, and that would be times m plus 1, 3, right? So this here, this is the case k equals 0, and then plus 2, 1, and then it would be m plus 2, 3. And this is k equals 1. All right, and that's the claim. Now, the good news is we actually know these numbers. 2, 0, our Eulerian number, is 1, and 2, 1, the Eulerian number, that is also 1. So we have really m plus 1 choose 3, and m plus 2 choose 3. All right, well, is that the answer? It turns out, yes, that is. But that's not normally the way you see it. So we're going to clean it up a little bit. What is m plus 1 choose 3? Well, it is m plus 1 times m minus 1, right? Because the rule is you start with the first term, and you're going to have 3 terms in the top, right? And you just go down by 1 in each step. And then divide by 3 times 2 times 1, well, that's 6. Plus, okay, start with m plus 2, m plus 1, m. Because you start with m plus 2, you're going to have 3 terms, go down by 1 at each step. 3 times 2 times 1 downstairs is 6. Now notice, they both have m plus 1 and m, so you can factor that out. They both have a 6, so you have a m plus 1 times m over 6. And what's left? Well, we haven't grabbed that m minus 1, so that's left. And we haven't gotten that m plus 2. That's still left. And, well, if we add those together, that's 2m plus 1, which leaves us with m plus 1 times m times 2m plus 1 all over 6. And that's the answer. So now, if you want to add up a bunch of squares, there's a beautiful formula for it. So it turns out that a bunch of squares has this nice expression. And I would consider this a fairly nice expression. You're like, okay, all right, I've seen that before. Come on, show me something I haven't. Okay, how about cubes? Okay, let's do that. Okay, so what do we have? 1 cubed plus 2 cubed all the way out to m cubed. All right, now this would be n equals 3. Okay, well, according to the formula, okay, so we come over here, and now we have n equals 3 here, so there's going to be a 3 upstairs. Then downstairs, well, it can be either 0, 1, or 2. And then this is going to be a 3 plus 1, which makes it a 4. So let's see, what do we have? We're going to have 3, 0, and then we're going to have an m plus 1, 4. Okay, this is our k equals 0. Then we're going to have a 3, 1, and it's going to be a m plus 2, choose 4. And this would be if k equals 1. And then we're going to have a 3, 2. And then it's going to be a m plus 3, choose 4. And this is if k equals 2. All right. And we know these things, right? We know these Eulerian numbers because we actually have the data. This is 1, 4, 1. So we end up with m plus 1, choose 4, plus 4 times m plus 2, choose 4, plus m plus 3, choose 4. All right. Is that the answer? It is. It is the answer. Now, this is not normally the answer we see, so let's clean it up, okay? Does it have a nice expression? And I will tell you at a time, it has such a beautiful expression. It's kind of almost too good to be true. So, but let's see what it is. Okay, let's see what it is. This will be good. Okay, so lots of math here to do. So, okay, so m plus 1, choose 4. So that's this upstairs. We're going to have m plus 1, and then that's where we start. We're going to have 4 terms in total. So go down by 1, m. Go down by 1 again, m minus 1. Go down by 1 more time, m minus 2. And then 4 downstairs, 4 times 3 times 2 times 1 means 24. All right, plus. Okay, here, similar thing, m plus 2. And then we're going to have m plus 1. And then we're going to have m. And then we're going to have m minus 1. 4 terms starting with m plus 2. Downstairs, 4 factorial, 24. And the last one, m plus 3, m plus 2, m plus 1, m downstairs, 4 factorial, 24. All right, good. Now, we see, hey, there's some things which are common. This m plus 1 and this m. They show up everywhere, as does the 24. Okay, so put that stuff out in the front. So what do we have? Well, we're going to have an m plus 1 times m over 24. Now, here we go. From the first term, m minus 1 times m minus 2 would be m squared minus 3m plus 2. Yep. M plus 2. Oh! What have I forgotten? What have I forgotten? Ah! Classic Steve. I forgot to mark down the 4! See, there's a 4 here. All right. So we're going to pretend like I didn't forget that. Okay. Yeah, that's going to matter. Okay. So now there's a 4, an m plus 2, and an m minus 1. Well, let's see. What will that give us? Well, it would be m squared, so then times 4, so that's 4m squared. Then there's going to be a minus m plus 2m, which would be plus m, but don't forget there's a 4. So that's plus 4m. Then a minus 2 times 4, makes -8. All right. Now we come to the last one, m plus 3 times m plus 2, which would be m squared plus 5m plus 6. Okay, so there we go. And now you're like, this answer is looking pretty good right now. Well, hold on. This is good stuff is about to happen. If we've lived a good, clean algebra life, and remember to write down that 4, good stuff is about to happen. All right, well, what's the good stuff? The 2, the 6, and the -8 cancel. That's pretty good. That's really good. What else? Well, we can group. M squared, 4m squared, m squared gives us 6m squared minus 3m plus 4m. That gets us to m plus 5m gets us to 6m. Well, that's what? Really, that's 6. M can factor out times m plus 1. That's pretty clean. That collapses really well. So there's a 6. That goes into 24, which leaves us with a 4 downstairs. And so and then we have an m. There's another m. There's an m plus 1. There's another m plus 1. So what we end up with is actually the following. We have m plus 1 squared, m squared over 4. Some people like to say, oh, this is really the same as m times m plus 1 over 2 squared. And there we go. There's the answer. That's really cool. And we can actually work it out. We have the tools now. Do we have to stop at cubes? No. See, that's the cool thing. We can now do arbitrary powers. Are we going to stop here? Yes! Not because we can't go further, but of course you can imagine the computation gets a little bit messier. But even though the computation gets messier, the basic idea is there. And it says, okay, we don't have to just fumble in the dark. We actually have tools, ways for us to answer these questions and get what we want. Isn't that nice? It's wonderful to be able to answer questions. And we almost have everything we need, by the way, to answer our big question, which is how many juggling patterns are there? And that's what we're going to finally answer in our next session. It's going to be good. All right. See you again.